Hello, in this video, I'm going to tell you about measures of variability or dispersion, and I'll go through some of the advantages and disadvantages and when we would use certain ones. So measures of variability or dispersion, those are statistics that communicate how far a data point is on average from the midpoint of the distribution. So we can only measure the variability of a data set if it is the type of data where we can calculate the average. So we can't use measures of variability for nominal or ordinal data because we can't find an average if it isn't numerical data like that. And so it's only used for that. So we are trying to see when we calculate the average, how far away are all of the data points spread away from that average? Like, are all the data points pretty tightly clustered around the average, or are they spread all over the place? So how much variability there is tells us a lot about how much the average actually represents the majority of that group that you're studying. So a few examples here that I'll discuss are range, mean deviation, variance of distribution, and standard deviation. So I'm going to run through all of those. So starting with range, it's the span of the scores in the distribution. So you simply subtract the lowest score from the highest score, and that gives you the range. So what is the range of scores? So in this example here, the highest score is 57 and the lowest is 12. It doesn't matter what order the data points are in, you simply subtract the lowest from the highest, and that gives you your range. It's not very useful, honestly. It's easy to calculate, which is its main advantage, but it's just not very useful. It's highly affected by extreme values. So if you have a very high score or a very low score that is an outlier, then that's going to significantly affect your range. It gives no information about where the different data points are located relative to the mean. So how much are they clustered or not? And it ignores all of the data points in the data set besides the highest and lowest. So not terribly useful, but very easy to calculate. Quartiles and percentiles. So I'm sharing these terms just because they're useful in understanding what we'll talk about on the next slide. So a quartile is referring to a fourth of a distribution of scores. So the first, second, third, and fourth quartile. The first is 0 to 25. Then the next quarter is the second. Then the third is 50 to 75. And then finally, the fourth quartile is 75 to 100%. So a percentile is a distribution value that says what percentage of values fall below it. So if you're 20th percentile, that means that 20% of the values fall below it. So like if you take a kid to the doctor and they're 20th percentile for height, it means that they are taller than 20% of the other kids in their bracket, in their age bracket that they're being compared against, and they are shorter than 80% of that same population. Okay, so interquartile and semi-interquartile range. So this is a way to make range a little bit more useful. So in this case, we're essentially cutting off the first quartile and the fourth quartile. So we're taking just the second and third quartile, so the middle 50% of your data set. That is the interquartile range. So if we chop off the highest 25% and the lowest 25%, then what we have left is the middle 50%, and that's the interquartile range. So it's more stable. It can be more useful than a just regular range because it cuts off all the extremes. So it's not really affected by extreme values unless there are a ton of them and they extend into that middle 50% of the distribution. But generally speaking, those extreme values, those outliers, are going to get chopped off when you get rid of the 25% on either end of your range. Semi-interquartile range is when you do the exact same thing and then you divide it by 2. It just makes it a little bit more resistant to the effects of extreme scores. So some advantages here. It's a good choice if you have a skewed distribution with a lot of extreme scores, because again, you're cutting out half the data in your analysis here. It's also not influenced by a small number of extreme scores, but the disadvantage is if there are a lot of extreme scores, it is affected. It's also resistant to the effect of truncated scores, so arbitrary cutoff points. So like if you're standing on 1 foot and you want to see how long each participant can stand on 1 foot for, if you say, okay, well, I'm going to cut everybody off at 2 minutes, now that becomes the ceiling of that data point. Nobody can score over 2 minutes, no matter how long they really could stand on 1 foot. And so that's a truncated score that's imposing an arbitrary or artificial high score. And so with an interquartile range, you're cutting off the highest and the lowest. So those highest scores that maybe could be much higher aren't going to be as important because those get all chopped off. They're not included here. Now, disadvantages, as I already mentioned, if there are a lot of extreme scores, it will affect your results here. And then the other big disadvantage is it only shows the relative position of each score. So we're not looking at how far each data point is from the average. Instead, we're just looking at where each data point is positioned relative to the center of the data. So it's not very useful in terms of seeing like how distributed are the data, like how far do the data points deviate from center, because it only shows the relative position of each score. All right, the mean deviation. It's the average amount of deviation from the mean using absolute values. So the deviation refers to how far off is this data point from the average. So from the center of our data, how far is this data point? That's the amount of deviation. So if a data point is above the average, then the deviation is positive. If the data point is below the average, then the deviation is negative. So when we add up all of the deviations, they will equal 0. Because the average is right in the middle of the data. It means that half of the data are going to be positive and half are going to be negative, and they will be equal. If we add them all together, we'll get 0. So we can't exactly find the average of the deviations if when we add them all up, they equal 0. So instead, for mean deviation, we use the absolute values of all the deviations. So the ones that are negative, we simply treat as positive, and then we find the average or the mean of those deviations. So if we look at our examples here, I gave a couple, just 5-point data sets, both that have an average or a mean of 3. So they have the exact same average, but I use different numbers in our set so that our mean deviation will be different. So first, we start with the absolute values of the deviations. So to find the deviation, I'm simply going to subtract the data point from the mean, or vice versa. It really doesn't matter which direction because we're going to use absolute values. We're not using negatives anyways. Okay, so for this first point, 1, that is 2 away from the mean. So my absolute value of the deviation is 2. If I just wanted to find the deviation, not the absolute value, it would be -2 because 1 is below the average. So anytime it's below the average, it's negative. If it's above the average, it's positive. Okay, so it would be -2, and then the next one would be -1, because it's 1 away from the average. But again, here I took the absolute values, so they're positive. And hopefully this also helps you see if we use the negatives, then we would have -2, -1, 0, 1, and 2. And if we add them all up, it's 0. So we can't get that average. Okay, so for our finding our mean deviation, so we're adding up all the absolute values of the deviations, and then we're going to divide by 5 because that's the number of deviations that we're averaging, and the answer is 1.2. Now, if we look at this second little 5-point data set, again, the average is 3, but now our deviations are a lot different because we had 3 points that were right on the average. They had no deviation from the average. So those deviations are all 0. Then if we find the deviation for this first point, it would be -2. And for this last point, it would be +2. But we're using absolute values, so we treat them all as positive. We add them all up, divide by 5, because that's our number of data points, and our mean deviation is 0.8. Okay, so the advantage here is that it's using the actual difference between each value and the mean. So we're finally calculating the actual differences between the data points and the average of the data. The disadvantage is that we're using absolute values, so it's limited in the application and how we can use this in other calculations, because we're using absolute values instead of the true actual value. So it really affects what we're able to use this for. All right, so then we get to variance. So in the last slide, we talked about solving the issue of adding the positives and the negatives, and then they equal 0. Well, this is a different way to solve that same problem. So for variance, there are a lot of different calculations, a lot of different formulas that you can use to find variance, and they should all roughly come to the same answers. But here, instead of taking absolute value to make the negatives positive, we're squaring them to make the negatives positive. Because anytime you square a negative number, the answer is a positive. So if we square all of the deviations, positive and negative alike, then all of those are going to be positive numbers. Then we can average those out. And that's what variance is. It's an average of all of the squared deviations. So all you need to do is find the deviation of each one and square it. And then you find the average of those squares, and that's your variance. Now, to make it slightly more complicated, when you're finding the average, normally when we do any average, you're dividing by the number of things that you're averaging. And for a population variance, that's still the case. Okay, so, but if we're using our sample variance to estimate population variance, and then we divide by n-1 instead of n. So basically, when you use a sample variance to try and estimate the population, it tends to estimate a little bit off. It tends to be a little bit skewed, where there is not an equally likely chance that your prediction is above or below reality. We want there to be an equal chance in either direction so that it's not biased. And so to do that, we subtract 1 when we're actually doing the math. So like if you have 5 data points, n is just 5. So normally to find the average, we're just dividing by 5. But what we're saying here is that when we're using a sample to estimate the population, then we would use n-1. So for 5 data points, we would divide by 4 because we're taking n, which is 5, and taking 1 away. We're dividing by 1 less. So it just sort of gives that variance that you're calculating a little bit of it inflates it just a little bit, and that provides a correction so that your population variance that you're estimating is more likely to be closer to the true value. So advantages here are that it treats all deviations as the same regardless of the direction of positive or negative. So we're not changing the actual values here. Like in the previous one, we were changing them to absolute values. So we're changing the numbers to make the math work. Here, we're able to use all the deviations as they are, as their true number, and find the true variance here. And then also variance is useful because we use it to calculate standard deviation, which is the most commonly used. And I'll talk about that on the next slide. Now, the disadvantages in variance, it gives added weight to the outliers because we are squaring the deviations. So anything that is a little bit out there is now going to be squared, and it's going to be exponentially out there, if you know what I mean. It'll be even more of an outlier after you square it. Now, variance also is really not very intuitive to interpret or understand when we're working with our data necessarily, because it's a very inflated number compared to the actual data that you're analyzing. So if you're looking at your raw values that you're analyzing and you look at your variance, those numbers are not going to be related. They're not going to make sense intuitively. Like we can't look at the variance and say, oh, that's how much difference there is, because it's squared, it's way inflated, so it's not very intuitive. And it's affected by an extreme score where the distance from the mean is very large, again, because it gives weight to outliers because it's squaring them. Now, if we take the variance, so again, it's squared, it's way inflated and way out there compared to the actual values that we're analyzing. So if we take variance and we find the square root, here, actually, I'll come back to this in a second. If we find the square root of it, that's our standard deviation. And that's why it's the most useful, is because we're finding the square root. It brings that number kind of back to reality. It's a lot easier to understand standard deviation in terms of the raw values that you're actually using to calculate. Now you can look at standard deviation and say, okay, here's on average how far from the average that these data points are. So I'm just going to swoop back here for 1 second. We're going to look at these quick little examples for variance. So again, this is the exact same data, these little mini data sets that I included on the previous slide. So again, both of the means are 3. And the deviations now, instead of absolute values of them, we're using the correct positive and negatives. So then if I square them all, then that's the result. If we square -2, we get 4. We square -1, we get 1, and so on. So that's why we square it. We're getting rid of all of the negatives by doing that. Okay, so you find the squared deviations, and then you are dividing by the number of data points, and that's your population variance. Now, again, if we're using a sample and we're trying to estimate the population variance, then instead of dividing by the number of data points, you're going to subtract 1. So remember, it's n minus 1 if we're using a sample variance to predict the population variance. Okay, so the sample variance, even though we're using all the same squared deviations, the sample variance will come out to be slightly higher than the population variance because we're making that correction so that we are not underestimating. Okay, and then if we look at the second example, again, there's our negative deviation there. Then we square them, add them together, and find our average. So in this case, the population variance is 1.6. And then the sample variance, again, slightly higher because we subtracted 1 when we did our dividing. Okay, so standard deviation, again, now once we have our variance, all we have to do is take the square root, and now we have our standard deviation. So much more intuitive, much easier to interpret and understand. This is the most common that is used when reporting the findings in research. Yeah, let's see. So if we look at our calculations, again, the exact same data points have been using. So we found our variance. In this case, I just used the population variance because I didn't think we needed both examples. So then all you have to do is take that result and square root it. And there you go, your population standard deviation. And then you would apply it the exact same way to find your sample variance. You would just use that sample variance number that we calculated on the previous slide. All right, well, thank you so much for watching this video, and I hope you have a great day. Bye.